So hello everyone.
Recording in progress.
We're going to discuss chapter 10, which is the dynamics of rotational motion. So in this chapter, you will learn what's meant by the torque produced by a force and how the net torque of an object affects the object's rotational motion. So you will know what this torque means. So a tendency to a body to a rotational tendency of body. Okay, if you remember force, if you apply a force, a body could translate or change in position linearly, but applying also a force could make a body to rotate, okay, depending on the position of the force you applied. To how this net torque of an object affects the object's rotational motion, how to analyze the motion of an object that both rotate and moves as a whole through space. Okay, how to solve problems involving work and power for rotating objects, and how the angular momentum of an object can remain constant even the object changes shape. Okay, so we have here the jugglers toss the pins so that they rotate in mid-air. Okay, what does it take to start a stationary object rotating or to bring a spinning object to a halt? So think about it. Well, introduce some new concepts such as the torque and angular momentum to deepen our understanding of the rotational motion. Okay. By the way, before you go to this, you proceed, you need to review the chapter one, vectors, the product of two vectors, which is the cross product of two vectors. How to do the cross product of two vectors. So here we have a range. Okay. So uh, it's loosening a bolt. Okay, you have a wrench which is loosening a bolt. Okay, so we have three forces that is being applied: FA, FB, and FC. Okay, so here we apply FA, force close to the axis of rotation, not very effective. So this is the axis of rotation of the bolt. Okay, you apply the force in this direction, you can see that this is not really effective when you apply a force from the axis of rotation with less distance compared to this f of b, which is farther from the axis of rotation, which is more effective, which is a greater distance from the axis of rotation. Okay, we note that distance as r. Okay, now we also have C, force directed towards the axis of rotation, which no effect. Okay, depending on where did you apply the force is the more effective would be your, what we call this one, loosening a bolt. Okay, so in this particular example, you can see that B is the most effective, more effective among these three forces, and FC is doing no effect in this kind of situation. Okay. So say for example we have a body. So we have here a rigid body or a body tends to rotate at, at this position at the origin O. This is the axis of rotation. It could rotate counterclockwise or clockwise. Okay. So here we apply a force. We call that force as the apply a force, and this line here. Okay, from the force, okay, this line here, we draw a line. We call that one as the line of action of F1. Okay. And then from the origin or from the axis of rotation, okay, from O to the line of action, okay, we call that one as the lever arm L1. And the torque, we denote that the torque is just equal to the force F1 L1. Okay. Applying L1, okay, we note that the system, if you apply F1, would rotate around this counterclockwise. Okay. So we note that the rotation from counterclockwise is what we call the positive torque. Unlike F2, if you rotate this one F2, okay, we have here the line of action, we have the lever arm, and the rotation tends to rotate clockwise. Okay, if clockwise, then negative torque. So again, the torque 2 is equal to the negative F2 times the lever arm, the force times the lever arm. Again, here an F3, a third line, the line of action of F3 passes through a point of the origin or the axis of rotation. So the lever arm and hence the torque is zero. So if your line of action passes this one, passes the axis of rotation, then what will happen is that there's no torque. This torque is zero. So torque could be positive if the rotation of the body, if you apply the force and it rotates counterclockwise, and negative it rotates clockwise. So this one, okay, the line of action, force of the line along which the force vector lies. The lever arm of the force is the perpendicular distance from the axis of rotation to the line of action of the force. Okay, the torque of a force with respect to O is just the product of the force and its lever arm. Okay, here we have three ways to calculate this torque. Okay, we have actually three ways to calculate this torque. So say for example, this is the axis of rotation. Okay, this is the axis of, okay, this one here, this arm here can rotate uh, in this axis of rotation, and this one is our, what we call this one, the force which being applied. Okay, so we have actually three ways to calculate the torque. Number one, okay, number one is that you put the vector, you use the definition that the torque vector is equal to R cross F. Okay. So by definition of our the cross product, so you put this one tail to tail. So this is your direction of your vector R. Okay. Okay. This is your vector R and this is your vector F. Okay. And this is your vector R. Okay. Here you will find that the angle between them is just phi in this particular situation. So if that's the case, then the magnitude of the torque, okay, the torque, the magnitude of this torque is just equal to the magnitude of R cross F. By definition, this is equal to R F sine of phi, where phi is the angle between R and F. So the second method is you use this definition F times L. Okay. So the torque, the magnitude of the torque is equal, this is actually the tau or the torque, we call this one tau. So here, you need to find the lever arm. Okay. So if this is the line of action, okay, line of action, then from the axis of rotation, we have the lever arm perpendicular to the line of action. Okay. So if this is phi, so here the line action, this L is just equal, if this is this magnitude of this R, so sine of that angle phi is just equal to the SOHCAHTOA, which is hypotenuse over SOHCAHTOA, which is adjacent, opposite over, which is opposite, which is L over R. So the lever arm is just equal to R sine of phi. So here the torque is just equal to the F times R sine of phi. Okay, so the third one is that you consider what we call this one, the the so you can see here that only this the F radial, so the force has two components, which is the radial and tangential. You can see here that only the radial tangential, the force tangential is doing torque. So this radial is not doing torque because you can see here from this example, force number 3, the line of action F3 passes through a point O because it passes through this point, the line of action of this one. So here, you use this definition that F tangential times R. Okay, so if you can see here, the F tangential is just equal to the F sine of phi. So radial is the cosine, the opposite is this one. So F sine of this angle phi here is equal times R. So this is the three ways to calculate the torque of the force. So my personal choice is number one because it obeys it goes back to the definition of the product of two vectors. Okay. So here, if you use your right hand rule, okay, you point your hand to the direction of R, okay, just like this one, R, and then okay, you use your right hand, and then your palm facing into the force. So this is what we call out of page, this direction torque. So please review your product of two vectors. Okay. So here, torque can be expressed as a vector using the vector product. So again, if you curl your fingers to the right hand in the direction of the force around the rotation of axis, your outstretched thumb points into the direction of the torque. So we discussed this one in chapter 1, which is the cross product of two vectors. So we have here a particular example on applying the torque. Okay. Uh, to, to- in example 10.1, to loosen the pipe fitting, okay, a weekend plumber slips a piece of scrap pipe over his wrench handle. He stands on the end of the cheater, applying his full 900 weight at a point 0.80 meters from the center of the fitting. So you can see it in the figure. So the wrench handle and the cheater make an angle of 19 degrees with the horizontal. Okay. Find the magnitude and the direction of the torque he applies about the center of the fitting. Okay, so let's use the definition number one, which we put this vector r, okay, tail to tail. So you can see here if uh, this is the vector r in that direction. Okay, r this is vector r, and this is the direction of the force. This is the direction of the force. Okay, vector. Okay, you need to find this angle here, phi. Okay, so since you are given a clue, okay, you are given a clue, just like this one. So this is the clue actually. Okay, so you have here 90 degrees, 90 degrees, and you have here 19 degrees. So meaning this one here is, okay, so that one here is actually 71 degrees. Okay, so 71 degrees. So if that is 71, so meaning if this is 180, so this one is 109 degrees. Okay, that one, your phi is 109 degrees. Okay, this is 71. So what I mean is this is 71 degrees and this is 90 degrees. So this is your R vector. This one here is 109 degrees. Okay, so from the definition, the magnitude of your torque, okay, is equal to the magnitude of R cross F. Okay, so here we have R. Okay, so we have R F sine of phi, which is R is 0.80 meters times 900 Newton, and Newton times sine of 109 degrees. Okay, so You try this one in your calculator. 0.80 times 900 times sine 109. So you have 680.7. 680 point 8 Newton meter. So this is your answer. So in your book is just 680. 680 Newton. Here, 680 Newton. So in three significant figures, so it should be 681. So 0.80, okay, times 900 sine 109. Okay, 109 degrees. 109 degrees. Okay. For the second definition, number two, okay, if F is just equal, L is just equal to the torque, the magnitude of the torque. So you need to find the line of action. So in this case, this is the perpendicular, this is the line of action. Okay. So this is your L. Okay, L. So L here, okay, if this is we call this one as uh the this angle here, phi, okay. So you want to find phi here. So actually, okay, if you use the angle 71, okay, the angle 71, this is lever arm L, okay, okay. So sine of 71 degrees is just equal to the opposite, which is L over the hypotenuse, which is equal to R. So L is equal to R sine of 71 degrees. So we have here F times R sine of 71 degrees. Okay. Here, F is 900 Newton times 0.80 meters times sine of 71 degrees. 900 times 0.80 sine of 71. So we have 680.8 Newton meter. So we use the Newton meter, not joules, because this torque is not an energy, or it's not a work. Okay, from the definition number three, so we have here the definition number three, which is the torque is equal to F, the tangential component times R. Okay. So here, the tangential, so uh, it has a component, okay, this force here as a component along this one, and component along this one. Okay, here is the F radial, and here is the F tangential. Okay, so if you use the 71 degrees, okay, if we're going to use this 71, the degree 71, so F tangential is just equal to uh, uh, so this is opposite 71 sine uh, uh, F tangential is just equal to F sine of 71 degrees. Okay, if you use this angle here, which in this little angle here, which is 90 minus 71, okay, you could also use F is equal to cosine 19 degrees. Okay. So cosine 19 is 0.9 and sine 71 is 0.9. So the same value. So here we're gonna use this sine 71. Okay, so we have here 900, or we're gonna use this one. You could also use this one. This 19 degrees from this angle here. Okay. So here, so let me so suppose uh this is the vector r, okay, and this is the f here, f, okay, f force, okay, and this is 90 degrees, okay. So we have f tangential here, tangential. So we know this is 71 degrees, and you know that if this is 90, so you have 19 degrees here, 19 degrees. Okay, so that is the f. This is the f tangential, f radial, and this is f tangential. So if you use this 19 cosine, if you use this 71 sine, so let's try this one. So we have f cosine of 19 degrees times set of r, which is 900 Newton, uh, cosine of 19 degrees times r, which is 0.80 meter, which is so 900 times cosine 19 times 0.8. So we have 680.8 Newton meter. Okay, so this is how to calculate the torque. How to three ways of calculating the torque. So please we will continue our discussion in the next video. So please like or click subscribe for more videos like this.